So hello everyone, this is lecture 10 for the quantum mechanics. In the last lecture we were studying about the matter waves and we were seeing the physical interpretation and we were seeing about the Max Born approximation which he gives that matter wave is nothing but probability wave and it represents the probability of finding the particle. So before moving forward, let me give you the solution, the question I have given you. So first question was find the de Broglie wavelength of electron whose speed is 10 by 8 and same for if speed is this. So by seeing the speed you can't know if this electron is the relativistic nature or not or non-relativistic. So what you will do here, so you will use the general formula to find the de Broglie wavelength, means the relativistic formula. That was this formula. Lambda equal to Sc by k plus 2 m naught c square, where this k is kinetic energy and m naught is rest mass. So what you will do, you will use this direct formula lambda equal to h upon p, where this mass is relativistic. So that will give you this formula. Now you know the speed, so just substitute it here. Either it can be 10 to the power 8 or 2 into 10 to the power 8. So given speed will be substituted here and you can find the lambda from here directly. Don't use this formula because this is for the non-relativistic case, but this formula is applicable for all the terms, all the values. If the speed is non-relativistic, then it will turn out to be this again. Okay, so just use this formula, you substitute the value of velocity and get the answer. Now same for this B part also. Now find the de Broglie wavelength of our 10 milligram. So weight will be 10 to the minus 3. That will give you in the gram. Grain of sand blown by wind at speed this. So speed is given and mass is given. So mv will give you momentum and lambda will be h upon p. So that's how you can find the value. Now find the de Broglie wavelength of the 40 kilo electron volt electron used in a certain electron microscope. So the kinetic energy or the energy is given. So what you will use, it was nothing but lambda equal to h upon p, and p is nothing but under root 2me, where e was energy. So to find the de Broglie wavelength, lambda will be h upon under root 2m multiply energy. So just substitute the value of energy and mass of electron and h, that will give you lambda. Find the de Broglie wavelength of 1 mega electron volt proton. So for proton, the energy is given. Use the same formula h upon under root 2me. So in place of energy you will write this and mass of proton will be written. So that will give you your answer. Now this is important question. A photon and a particle have the same wavelength. When wavelength is same, so we need to see the linear momentum of photon and particle. So relation is lambda equal to h upon p. So when lambda is same, so it will be h upon p1 equal to h upon p2. So p1 will be equal to p2. So momentum will remain same for photon and particle. Now B part is compare the photon energy with the particle's total energy. So we need to compare the energy. Now see, if we talk about the energy, then for the photon it is nothing but h nu, sc by lambda. But if you talk about the total energy of a particle, so that will be given by this formula, rest mass energy plus kinetic energy. So rest mass energy for that particle and kinetic energy is nothing but p square by 2m, and p can be written from here h by lambda. So you will get this will your total energy for a particle, m naught c square plus h square by 2m lambda square. And for photon this will be this sc by lambda. Now see, this value is greater than this one for the same lambda. So you will say that the energy of particle, total energy of particle will be greater than photon for the same wavelength. So if we are comparing the total energy, then this will be greater than this. But now in C part, compare the photon energy with particle's kinetic energy. Now we need to compare kinetic energy only. So see, for the photon, energy will remain same as sc by lambda. But for the particle, this will be your kinetic energy. Now see, this is lambda square and this is lambda. And here this mass is also involved for the particle. And here is no mass. So lambda is same. So this square term will be greater than this one. And this mass multiply will be make it more bigger than this. So this whole value will be less than as compared to this. So kinetic energy of particle will be less than the photon's energy. So that will be your answer for this C part. Now an electron and a photon both have kinetic energy equal to 50 kilo electron volt. So kinetic energy is given for both photon and electron, both have same energy. Are the de Broglie wavelength equal? What are the values of the wavelength for each? So we need to find the de Broglie wavelength for them. So here kinetic energy is given, so we'll use this formula for the lambda. Relativistic formula Sc over under root k plus 2 m naught c square. Now see, for the photon this rest mass is 0. So that will give you lambda equal to sc by k only, and for the particle or the electron will have some rest mass, and this kinetic energy will be same. Now this lambda will be different for both of them, because for a photon it will be sc by k only, and for the electron it will be sc by k square plus 2, this will be mass of electron, c square. So this will be somehow different from them. So lambda will be different for both photon and electron, and by substituting the value you can find the lambda also for the different photon and the electron. So that's it for the questions. Now let's move forward. So we were discussing about the probability wave. So Max Born said that we have a matter wave is nothing but a probability wave which denotes the probability of finding the particle, and a probability wave should be look like this, because where this particle, this graph should be go like this, and to infinity it will go at 0. That is the probability, and this somehow looks like a wave packet. So our matter wave should be some kind of wave packet. So we don't know actual physical interpretation, but we must know the mathematical interpretation to go forward. Okay, so why our matter wave can't look like this? So let's see one more example why we can't express our matter wave in this form. So see, if we assume our wave function as a cos ks minus omega t, and waves look like this, so this will be your equation. Now why this is not allowed? So this is not allowed representation of wave function of free particle. Then why? Let's see, if this is your wave, then this phase will remain constant, this is phase of the wave, so kx minus omega t will be constant. Now find the dx, so it will be means differentiation, so it will give you k dx minus omega dt equal to 0. From here dx by dt will be omega by k, and this is nothing but phase velocity for the wave. So for a particular wave you have the phase velocity, so omega by k. Now let's find the velocity associated with the particle with this wave. If we assume this is your matter wave, then let's find the velocity for the particle associated with it. So let us evaluate Vp for a de Broglie wave associated with the particle with linear momentum p. The energy will be and energy E. So energy is nothing but p square by 2m. So in place of means Vp can also be written in this form, because you can multiply h cut here, so it will give you h cut omega divided by h cut k, and this is nothing but E. This is p for the particle. Now E is p square by 2m. So substitute here p square by 2m, you will get Vp equal to p upon 2m. This is nothing but p is mv, so it will give you v upon t. So now for the particle you will have velocity v by 2, and for the wave you have velocity v. So Vp here is v by 2 and here it is v. So see, there is difference, means this is not a digestible thing, that particle having velocity half and wave having velocity v. So it can't be different, it should be same. So that's how we can say that we can't say or describe our particles matter wave in this form. So this is not a valid form. So what can be? Now as we have seen that this is look like a wave packet, so let's find the velocity for a wave packet also, if it validating this thing or not. So let's say we have this wave packet, and this has the group velocity Vg. So what is group velocity? The complete wave packet velocity is called the group velocity. At what speed this whole packet is moving is v group. So let's say our particle is denoting by this wave packet, and let's find the velocity. Now we know for the group velocity the expression is d omega by dk, and we know E equal to h cut omega, p equal to h cut k. So d omega will give you de by h cut, and dk will give you dp by h cut. Now from here this Vg will be de by dp. Now you know for energy from here p square by 2m, substitute here, you will get this expression p by m. Now p mv, so m will cancel out and you will get velocity as v. Now our wave and the particle have the same velocity v. So see, this wave packet speed is came out to be v, and this particle's velocity is also v. So this satisfied or validates that this particles, the wave associated with this particle must be look like a wave packet. Okay, now if we understand this thing, means we don't know the actual physical interpretation, but we are somehow trying to understand this by the mathematical ways. Okay, so we come to this conclusion that our matter wave looks like a wave packet. So must means if it is wave packet, then we must understand the wave packet now. So I already described this wave packet in the solid state physics, but here also I will give you some idea. So let's see something about some things about this wave packet. So what is a wave packet? When we have multiple waves and they superimpose, then they superimpose to give a resultant wave, and that is called means that can be made of a wave packet, means that can be wave packet. So let's say we have these two waves and their wave equation are given by this, means wave function are given by this. So for the first one, the psi1 equal to a sin k1x minus omega 1t. For second one, it is a sin k2x minus k omega 2t. So we have these two. Now the resultant wave will be psi1 plus psi2. So you will use the trigonometric identity here. So it will be sin a plus sin b will give you 2 cos a 2 sin a plus b divided by 2 cos a minus b divided by 2. So it is this 2a sin a plus b will give you k1 plus k2 divided by 2 omega 1 plus omega 2 divided by 2, and this is cos a minus b means k1 minus k2 and omega 1 minus omega 2 divided by 2. So this will be your expression. Now we have assumed these omega 1 and omega 2 are these 404 and 400 multiplied 2 pi hertz. Now if you see this resultant wave, now we have here two sinusoidal waves because of this cos and the sine. Now if we means visualize this wave in the plot, or we plot this curve, then we will see that we'll get this kind of wave. Means if this is your amplitude, then this is varying with time, means this will go like this, and this is also varying with time. So we have two different things here. Now let's find the velocity for these two different things. Means here you will get this omega 1 minus omega 2 divided by 2 frequency, and here you will get omega 1 plus omega 2 divided by 2 frequency. So see, this frequency is associated with the inside wave, means in the with the singular waves, or this kind of singular waves, individual waves. But this frequency omega 1 minus omega 2 divided by 2, this associated with the complete packet. So from here we will get the velocity for the wave packet, and here we will get the velocity for the particular wave, and that we call the phase velocity, and that is called the group velocity. So let's see, this phase should remain constant for this one. So let's say this is constant. Now find the dx dt, means do the differentiation. So this will give you dx by dt equal to omega 1 plus omega 2 divided by 2 k1 plus k2 divided by 2. Now these omega 1 omega 2, all the frequencies are nearby together, means they are almost equal, 404 and 400. So we can write in place of this omega in place of k. So this is nothing but phase velocity. So we write this as means this is equivalent to Vp. This is what the speed of this wave, omega 1 by k1 gives the velocity for this wave, and same for this omega 2 by k2 will give you the wave, speed for this wave. So that's why we are getting the same expression almost. So that's why we called this velocity as the phase velocity, or the velocity of these individual waves. Now let's find the velocity for from this second term. So this is also phase, so this will remain constant. Now from here you will get dx by dt as omega 1 minus omega 2 divided by k1 minus k2, and here it will give you like dl omega by del k. So this expression is same for the group velocity. So this will give you the velocity of the wave packet. This is called the group velocity, means at what speed this complete wave is, this complete packet is traveling. So that is group velocity. So remember these expressions for the group velocity and phase velocity, and what is the difference. So you must note that. Now let's find some relation between these group velocity and the phase velocity. So we know this Vp, phase velocity, is nothing but omega by k, and Vg equal to d omega by dk. From here omega equal to Vpk. Put it here and differentiate. Use the product rule, it will give you Vp plus k dVp by dk. Now we know k is nothing but 2 pi by lambda. Then dk will be minus 2 pi by lambda square d lambda. Then substitute this value here in place of dk. Then you will get this value, Vg equal to Vp minus lambda dVp by d lambda. Now remember this relation. This is very important relation between the group velocity and the phase velocity. When this dVp by d lambda equal to 0, then we call the medium as the non-dispersive medium, because then this Vg will be equal to Vp when this will be 0. So the medium will be non-dispersive. But when this is not 0, then it will call the dispersive medium. Okay, and Vg won't be equal to Vp. And there is all two more cases. When this dVp by d lambda is greater than 0, then this Vg will be less than Vp, and we call that as normal dispersive medium. And when this dVp by d lambda is less than 0, then this Vg will be greater than Vp, and we call that anomalous dispersive medium. So remember all these points I told you. Okay, these are very important points. So question can be framed from here. Now let's see how we describe this matter wave now. Means here we have taken these two single waves. Now this matter wave, if it is a kind of wave packet, then it must be made up of a large number of waves, large number of individual waves. So let's visualize this. So it must be made up of these infinite number of waves. So that must give us our wave function. So now our target or aim is to find the wave function for the matter wave. So see, this wave can be represented in this form. This is some constant and exponential I k1x minus omega 1t. For second one it will be k2x minus omega 2t, and for third one it will be like this, and for one then it will go to nth terms. So these are n waves. Now see, we need to sum them, means we need to take the summation of all these. So this summation is somehow can we find it from the Fourier series. So we know about the Fourier series. It looks like means what is Fourier series? So any function fx on the interval minus L to L can be expressed in the form of Fourier series. So Fourier series is nothing but it is expression means any fx function which is periodic can be expressed in the terms of cosine and sine. So this is called the Fourier series. You can see my lectures on the Fourier series in the mathematical physics. So there I have explained all the things about the Fourier series. So here I will give you just a small idea. So Fourier series is nothing but you can express any function in the form of this. You need to find this a naught, an and bn. So they will be a naught equal to this 1 upon 2l minus L to L fx dx, an equal to this cos n pi L by L x dx, and this. So a and bn, these are the coefficients. You can find them and just substitute here. That will give you your fx. So that's how you can express any function in this form. Now there I already told you in the lectures that this Fourier series in the complex form can be written in this form. So complex form of Fourier series is nothing but this: fx equal to n minus infinity to infinity cn exponential I n pi x divided by L. So this is the complex form of Fourier series. Now where this cn is some constant or the coefficient, so how you can find this value? So this cn is 1 upon 2l minus L to L fx exponential I n pi x divided by L dx. Now see, if we make this cn somehow equivalent to this phi 1, phi 2 and phi n, then this cn here and the addition with all the waves will give you fx. So we will compare this fx with the wave function and cn with the individual wave function. So how can we compare them? So for this you need to eliminate n and cn in the favor of new variable this k and fk. So now in the Fourier series we will remove this n and cn and we will replace them with this. In place of cn we will write means fk will be equal to under root 2 upon pi cn. So this root 2 upon pi is just for the simplification or calculation. Otherwise it is just we are taking cn as fk and k as n pi by L. So it is nothing but fk equal to under root 2 by pi L cn. Now what is the value of cn? Cn is this 1 upon 2l, this one. So in place of this we will write this 1 upon 2l minus L to L fx and the exponential term. So L will cancel out and you will get 1 upon 2 here. So root 2 will cancel out, it will give you 1 upon root 2 pi. So you will get this expression fk will be 1 upon root 2 pi fx exponential minus I kx dx. Because where you are having this I n pi x by L, so in place of n what you will substitute here? N equal to lk by pi. So when you write lk by pi, so it will cancel out, pi will cancel out, L will cancel out, and you will get this thing only, fx exponential minus I kx dx. So this will be your fk. Now this is how you can express this your wave function, means now this is a function for individual waves. Now the summation of this, now you expressed your individual waves in this form. Now what you will do, you just find the Fourier transform of this, because this inside fx is nothing but your wave function. So when you find the Fourier transform is nothing but it is just a change of these things. In place of fk it will be fx, and in place of fx it will be fk, and in place of dx you will get dk. So that's how it will change it. So when you do the Fourier transform you will get fx, that is wave function, is equal to 1 upon root 2 pi sigma minus infinity to infinity fk exponential I kx del k. Now see, this is for this expression will give you your wave function. So we find this from the Fourier series. So see, this is for a discrete values of k, that's why we use the sigma sign. But see, if this L tends to infinity, means because we in the matter waves, what we do, we take the complete axis, and that's how we describe the wave packet. So L tends to infinity, minus infinity to infinity, then what happens, this k is tending to 0. So when this k is tending to 0, then it will become continuous, means now k is not discrete anymore, means we can't take these values k1, k2, k3, k4 for different waves. Now this k should be continuous, okay, and when this k is continuous, you can't separate them, then you can't take the summation, then this summation will turn out to be integration. Now this summation will remove by integration. So what will be your wave function now when this is continuous? Then this will be your wave function fx 1 upon root 2 pi fk exponential I kx dk, and this is nothing but Fourier series of a function, and fk is nothing but this. So just summation is removed by integration, and this will give you your wave function. So for the continuous k, this will be your values, and let's see this wave function. Now this will be your wave function. So localized wave, what is a localized wave packet? So wave packet psi xt can be constructed by superposition of large number of monochromatic waves. This is what we just discussed. It is just a definition or statement. So this wave function can be constructed by superposition of large number of monochromatic waves of continuously varying wavelength on k or k value. So k value is continuously varying, then we can write this wave function as 1 upon root 2 pi minus infinity to infinity phi k exponential I kx minus omega t dk. This phi k represents the individual waves. At t equal to 0, this psi x is nothing but 1 upon root 2 pi phi k exponential I kx dk, and phi k is nothing but this, and this is Fourier transform of psi x. So remember these results. These are the values of wave functions, and these are for the continuous values of k. But in the quantum mechanics, we will study the pure states or the eigenstates. We don't study this continuous values. We will study the discrete values. So how we will study them? Now in place of the complete integration, we will take these separate values, some pure states, and these are nothing but eigenstates. If these are your eigenstates for the quantum mechanics, we will study what are eigenstates. Here just to remember what I am telling you. If these are your eigenstates, then your wave function can be written in this form: C1 phi1 plus C2 phi2 plus C3 phi3, because these phi1 phi2 phi3 are linearly independent of each other and perpendicular to each other. So that's how you can write your wave function. And your wave function is nothing but summation of Ci phi I, where the C1 C2 C3 are constants, and these are your individual wave functions. So this psi x is nothing but summation of all these wave values. So in the quantum mechanics, you will see this cat and bra notation. So this will be your psi, and this can represent it, this thing can represent it in this form also: sigma Ci and phi I, this bracket close. So this will, we will study this thing in the quantum mechanics, not this continuous terms. But this is, you must know this you must know this thing for the general knowledge. So it can be asked in the interview that how you can see your wave function from the Fourier series. So you must know this thing. So in the next lecture, we will see about the wave function. We will draw for the discrete values or the pure states. Then we will move forward for the with the Born's interpretation of wave function. Okay. So we will see some more things about the probability. So that's it for today. Just to revise this lecture. If you are having any doubt, put it in the comment section. Thank you everyone.